Hello, my name is Inshira binti Abdullah and my metric number is 202921 for the subject PHY4301. For this subject, we have been given an assignment to teach on how does some instruction in the assembly language works. So for this particular assignment, I have picked 7 different instructions that I'm going to explain one by one briefly, and hopefully it will be informative and will be understood by everyone that is watching my video. So firstly, I'm going to tell you what I chose to explain for this assignment. Firstly, I chose add instruction, then sub instruction, mul instruction, diff instruction, then we'll move on to logic instruction. There are 3: N, OR, and XOR. Firstly, add instruction. What is add instruction? For the syntax, it's supposed to be at, destination, comma, source. It is used to add 2 operands, and the operands can be in register form or in memory. Flags may be changed by your result of instruction, such as zero flag, sign flag, auxiliary flag, carry flag, and parity flag. Those might change depending on the result that we get from this instruction. I'm going to show you an example that I did before this by using the emulator that I've screenshot earlier. I'm showing you a very simple code. In the first line right here, you can see that I assigned 11 hex into AX, and AX and BX right here is they are registers. So in the second line, I assigned 14 hex into BX, and on the third line, I'm using add instruction where add AX comma BX right here. At AX will be the destination and BX will be source. So moving on to this, when I emulate this code right here, you can see that AX changed into 25 because adding 11 hex with 14 hex will give you 25 hex as the result, and carry flag, zero flag, sign flag, overflow flag, parity flag, auxiliary flag, all of them are 0. You can determine the flags by converting this hex into binary, and from that you can see what are the flags that are triggered by the result. Next, we move on to sub instruction, and the syntax is similar, very similar to add instruction. First, you have to type in sub, then your destination, comma, and source. Basically, what this instruction do is destination minus with source. We can see it in the next slide. And there are steps when executing sub instruction. You can take two complements of your source operand and then you add it to the destination operand. Lastly, the third step is to invert the carry. I'm going to show you what I did in the emulator by using this instruction. Just a simple instruction. Firstly I did this uh, code right here where I assign 22 hex into AX. And from the second line, I just subtract 12 hex from AX. Then I got the answer, which is 10 hex from AX. Actually, this is also another way to do this sub instruction. You can right away just subtract from your register by using another value. You can just right away subtract this, but also you can do this kind of code where I assign 55 hex into AX, then I assign in second line you can see that I assign 1E hex into BX and subtract BX from AX. This is a code that I usually see in my textbook and also slides. This is the usual ones. I convert 55 hex and 1E hex into binary because I want to see the result of the flag that triggers this. Apparently, only auxiliary flag that is 1. Your AX value will change because this one is a destination. I have moved, I have minus 55 hex from, I have minus 1E hex from 55 hex. That will give you 37 hex, and the computer will store it to AX. And here you can see that it's here in AL because it's the lower part of byte for AX. Next, we'll move on to mul instruction. Mul instruction is basically the multiplication in assembly language. There are three cases of mul instruction, which is byte multiply with byte, word with word, and then word with byte. But before that, you have to know that when multiplying 8-bit numbers, you will generate 16-bit products. And then the multiplication of 16-bit numbers will generate 32-bit product. For this case, it's actually 8-bit numbers multiply with 8-bit numbers that will produce 16-bit product. And one of the operand must be stored in AL register because 8-bit will definitely be stored in AL, the lower byte of AX register. And then the second operand can be registered in a register or in memory, and the result will be stored in AX. This is because your product is 16-bit, and the result will not fit in AL. Thus, it will have to be stored in AX. Firstly, I assign 1B hex into AL. Then AL and BX are register, and 1E hex into BX. Then I mul BX for byte times with byte. Just now we know that the first operand must be stored in AL register because 1B hex is 8-bit. And then 1E hex is also 8-bit, but it can be stored in BX because it fits there. And then I multiply it, we will get 16 bits product. From here, we can see that it's stored in AX because the result is 3 to A, where 8-bit will be stored in AL, and the higher bit will be stored in AH, thus everything will be stored in AX. Second one is word multiply with word. Word multiply with word is multiplication of 16-bit numbers, and that will generate 32-bit product. So one of the operand must be stored in AX register. The second operand can be stored in register or in memory. And for the mul instruction, the result can be stored in AX and DX. This is interesting because 16-bit of numbers will generate 32-bit product. So for 32-bit product, it will not fit in AX alone. So you have to store it in two register, which is AX and DX. So the lower word will be stored in AX, and the higher word will be stored in DX. We will see it now using the emulator. For this word 2378 hex, I store it in AX, and also 2F79 hex in BX. Notice that I am storing in AX and BX, which are registered. You can also use memory for this, but I didn't store it in AL, BL because it won't fit there. And this third instruction, mul BX, the result of multiplying AX and BX will have 693CBB8 as the result. So that is huge number, and it's more than 16-bit product. So you have to store into different register. So the higher word will be stored in DX and the lower word will be stored in AX. Lastly, for word times with byte. Word is 16-bit number and byte is 8-bit. For this case, it will be the same as word times word because the product will also be more than 16-bit, and after the multiplication the result can be stored in AX and DX. AX will hold the lower word while DX will hold the higher word. L contains byte operand. AH must be set to 0. This one is for the byte actually, because for word you have to store it in BX, AX, because it won't fit there. Okay, for this, of course, for AL, I stored this in AL, and AH will be 0. And the second line, 2F79 hex, I stored it in BX. You can store it in other register or in other memory. The result will be stored in both DX and AX, just like word times with word. Fourth instruction, I chose div instruction. Div instruction is basically the division in assembly language. And there are 4 cases of div instruction. First one will be byte over byte, word over word, word over byte, double word over word. For div instruction, immediate division is not available, An interrupt is generated when an error occurs. Uh, two of the error will be divide with zero, um, and divide overflow. I'm going to explain what is divide overflow. I type this instruction right here where 41 hex is assigned to AX, 2 hex is assigned to BL. If you realize it, this syntax is just the same as the ones in mul instruction. Uh, and 41 will be stored in AX and 2 hex will be stored in BL. From this, we can see that 41 is much bigger than 2 hex, so you will have overflow. Divide overflow is when the quotient is too large for the assigned register. The result of this is 120 hex. For the last bit, it's stored in AL and the first few one will be stored in AH. Because if AX is holding a very large value and if we divide it with very small value, it will be difficult for AL to handle the number, and that is when we get divide overflow error. This is the example, the same one that I used in the previous slide. Mm, 41 hex is assigned to AX and 2 hex is assigned to BL, then I divide BL. Only flag that is uh, generated is interrupt flag because it's error, and just now we have discussed that interrupt will be generated when there is an error. There are three instructions that I will be explaining to this. First one will be AND, OR, and XOR. For AND instruction, the syntax will be AND, destination, and source, and the operands must be in same size. The operands can be in memory or registered. This is the logic table for AND. For AND, carry flag and overflow flag will automatically be changed to 0 because there's no carry and there's no overflow in this. But for parity flag, 0 flag, and sign flag, there will be changes depending on result. I have done this by using the emulator. Just for example, I assigned 36 hex into AH and 1AH into BH, then and AH, comma BH. This is the one that I did, and this is those values but in binary so that we can see how the flags are affected. And here it's true that carry flag and overflow flag is 0, but the only one is parity flag. Parity flag is when the computer processes indicates that if the numbers of set bits is odd or even in the binary representation, such as this in the operation or instruction, the destination operand can be a register or in memory, and the source operand can be in register or in memory of immediate, and CF and OF will reset to 0, just like AND instruction. And this is the syntax. Also the same as AND. And this will be the logic table for OR instruction. This is the results of using the emulator, and also this is when I use binary. And also for OR instruction, you can use it to test for 0 operand. You can use it, the syntax will be or BL or AX comma 0, then you can make the 0 flag becomes 1. It will trigger 0 flag if um, all of the result will be 0. And lastly, XOR instruction. It sets the result bits to 1 if they are not equal, otherwise will reset to 0. And flags are set, such as and the same rules as and or instruction. This is the logic table for XOR. I have used this instruction to clear the contents of register by XOR in itself. Uh, as you can see right here, that I assigned 64 hex into BH and then XOR PH, BH, where from this result right here is 0, because you can see from the table here, the only one that is set to 1 is when um, there are different numbers that only will set to 1, but obviously all of this is not, so 0 flag will be set to 1. And also parity flag, actually you can see the flags from the emulator itself. Also, there is another way we can use XOR instruction is when we toggle bits of an operand by toggling the register. It will cause it to change the opposite value and all the other bits will remain unchanged. That is also one of the way we can use XOR instruction. And that is it for my presentation. Thank you very much.